Hello, welcome to my channel. This channel's for educational purposes, and we focus on theories of everything primarily that are obscure and marginal, but powerful and would benefit learners. So today is video number 215 on the reciprocal system of theory. And this is a system of theory, or a theory of everything, that was first arrived at by Dewey B. Larson back in the 20th century, starting way back in about 1930 up until his death in 1990. He put out a lot of books, a lot of articles, gave a lot of talks, didn't get a lot of traction. Not so much because his theory wasn't viable, but just you have to kind of unlearn a lot of legacy science, and there are certain complications with Larson's theory that just make it difficult to get into. Part of it is his writing. He writes well, but he doesn't really teach well. And so his information is all there, but it's kind of difficult to extract it. It's very difficult to single-handedly overthrow an army of scientists, regardless of who has the truth or not. The scientists generally have the equations. They can get the right answers, but they do not know why those answers work. They do not know how they got those answers. Larson solves the conceptual problem. He can tell you why these things are the way they are, but very few people have listened. So the basic idea behind Larson's theory is that this is a universe of motion, not a universe of matter, not a universe of energy, but a universe of motion. Matter and energy are merely two different kinds of motion. Motion is the relationship between space and time. Space and time are the same, except that they are reciprocals of each other. Motion is a fraction. Space and time is the numerator. Space or time is the numerator. Time or space is the denominator. But time or space both have their coordinate aspects, meaning that they come in 3 or more dimensions. Coordinate space, x, y, z coordinates. We are familiar with that. Coordinate time, not so much. 3 or more dimensions of time. And then clock time, we are familiar with that. The clock is always getting later and later and later. The flow of time. But then there is also clock space. Space is always getting farther and farther and farther apart. That is a scalar motion in space, which you can envision by using a balloon and a magic marker. Put some dots on the balloon, blow up the balloon, all the dots are moving away from each other. You could also picture it in the Hubble telescope, discovering that all of the distant galaxies are moving away from each other. That is the flow of space, or clock space. Then you have the discrete unit postulate. Both space and time come in chunks. They are not continuous. They come in very small chunks. Exactly one chunk of space in one chunk of time is the speed of light. The speed of light then is the midpoint of the universe. Not like Einstein says that the speed of light is the maximum speed of the universe. That's because Einstein only knew about 1/2 of this universe. He knew about the half that Larson calls the material sector, wherein the speed of everything is moving slower than the speed of light. However, there is another half of the universe that Larson calls the cosmic sector. And the cosmic sector is where everything is moving faster than the speed of light. Speed of light is actually the minimum speed of that universe. We know very, very little about the cosmic sector. However, since we know a lot about the material sector, because that's where we make our observations and measurements, and that's where the legacy scientists have made whatever progress they've made, all we have to do is extrapolate, because what's going on in the cosmic sector is identical to what's going on in the material sector on a grand scale, except that you have to invert the roles of space and time. The simple example is just what we were talking about with coordinate space and clock time. That is what we recognize in the material sector: 3 dimensions of space and progressing time. But if you reverse the roles of space and time, you get what's going on in the cosmic sector: coordinate time and clock space. 3 dimensions of time and progressing space, always getting farther and farther and farther apart. Those are, the parameters of the cosmic sector. Now, we're looking at Larson's 1979 book that's called Nothing But Motion, and this is primarily on atomic physics. We're in chapter 18 called simple compounds is what I believe it is. And so for Larson, we've got, he went through his explanation of atoms. Atoms are combinations of motions. There are 2 photons at the core of every atom, so to speak. And these photons are simple harmonic motions, wave-like motions, and they are the combination of 2 other kinds of motion in Larson's system: 1 translational motion and 1 vibrational motion, 90 degrees offset from the first motion. Some of Larson's followers actually claim that they are the wave motion, the simple harmonic motion, is product of a birotation. 2 counter-rotating motions also yield a simple harmonic motion. So there is a dispute there, which we will touch on fairly soon. But that is basically the photon, and then the photon needs to be rotated at least in 2 separate dimensions, and then you get matter, atoms. And now he's talking about compounds, so molecules, 2 different atoms, 2 or more different atoms combining together. And so now we started this chapter yesterday, and so he's getting up to discussing some more aspects of this process of compound formation. All right, we'll give it up to Mr. Larson here in his own words. As has been stated, negative rotation in the electric dimension of an atom is admissible because the requirement that the net total rotational displacement must be positive in the material sector can be met as long as the magnetic rotation is positive. In the time region, inside unit distance, however, okay, so just recall that the time region is the region inside of space, okay? Space and time both have discrete units. And so when you have less than 1 unit of space, you no longer have space. You only have time. And when you have less than 1 unit of time, you no longer have time. You have space. And so this sets up sub-regions within the material and cosmic sectors. So within the material sector, you also have what is called the time region. That is the region that is within 1 unit of space. Okay, so, and that is the region of atoms. That's where atom formation is occurring within the time region. Okay, in the time region, and that obviously in the cosmic sector, That is where you have the formation of cosmic atoms, or the legacy scientists call it antimatter. Okay, in the time region inside unit distance, however, the electric and magnetic rotations act independently. Here, the presence of a randomly, now when he says electric and magnetic rotations, he's referring to one-dimensional and two-dimensional rotations. Here, the presence of a randomly oriented electric rotation in time makes it impossible to maintain a fixed interatomic equilibrium. Any relation of space to time is motion, and motion destroys the equilibrium. But an equilibrium can be established in certain cases if both of the interacting atoms are specifically oriented along the line of interactions in such a manner that the negative displacement in the electric dimension of one atom is counterbalanced by an equal positive displacement in one of the dimensions of the second atom, so that the magnitude of the resulting relative motion is zero with respect to the natural datum. Or a multi-atom group equilibrium may be established where the total negative displacements of the atoms with electric rotation in time are exactly equal to the total effective positive displacements of the atom with which the interaction is taking place. In these cases, there is an equilibrium because the net total of the positive and negative displacements involved is zero. Alternatively, the equilibrium may be based on a total of 8 or 16 units, since, as we have found, there are 8 displacement units between one 0 point and the next. A negative displacement x may be counterbalanced by a positive displacement 8 minus x, the net total being 8, which is the next 0 point, the equivalent of the original 0. As an analogy, we may consider a circle, the circumference of which is marked off into 8 equal divisions. Any point on this circle can be described in either of two ways, as x units clockwise from 0, or as 8 minus x units counterclockwise from 8. A distance of 8 units clockwise from 0 is equivalent to 0. Thus, a balance between x and 8 minus x with the midpoint at 8 is equivalent to a balance between x and negative x with the midpoint at 0. The situation in the interatomic space-time equilibrium is similar. As long as the relative displacement of the two interacting motions, the total of the individual values amounts to the equivalent of any one of the 0 points. The system is in equilibrium. Let me try reading that last sentence again. As long as the relative displacement of the two interacting motions, the total of the individual values, amounts to the equivalent of any one of the 0 points, the system is in equilibrium. Because of the specific requirements for the establishment of equilibrium, the components of combinations of this kind, molecules of chemical compounds, exist in definite proportions, each n atoms of one component being associated with a specific number of atoms of other component or components. In addition to the constant proportions of their components, compounds also differ from mixtures or alloys in that their properties are not necessarily similar to those of the components, as is generally true in the all-positive combinations, but may be of an altogether different nature, as the resultant of a space-time equilibrium of the required character may differ widely from any of the effective rotational values of the individual elements. The rotational displacement in the dimension of interaction determines the combining power or valence of an element. Since the negative displacement is the foreign component of the material molecule that has to be counterbalanced by an appropriate positive displacement to make the compound possible, the negative valence of an element is the number of units of effective negative displacement that an atom of that element possesses. It follows that, with some possible exceptions that will be considered later, there is only one value of the negative valence for any element. The positive valence of an atom in any particular orientation is the number of units of negative displacement which it is able to neutralize when oriented in that manner. Each element therefore has a number of possible positive valences, depending on its rotational displacements and the various ways in which they can be oriented. The occurrence of these alternate orientations is largely dependent upon the position of the element within the rotational group, and in preparation for the ensuing discussion of this subject, it will be advisable for convenient reference to set up a classification according to position. Within each of the rotational groups, the minimum electric displacement for the elements in the first half of the group is positive, whereas for those in the latter half of the group, it is negative. We will therefore apply the terms electropositive and electronegative to the respective halves. It should be understood, however, that this distinction is based on the principle that the most probable orientation in the electric dimension considered independently is that which results in the minimum displacement. Because of the molecular situation as a whole, an electronegative element often acts in an electropositive capacity. Indeed, nearly all of them take the positive role in chemical compounds under some conditions, and many do so under all conditions, but this does not affect the classification that has been defined. There are also important differences between the behavior of the first four members of each series of positive or negative elements and that of the elements with higher rotational displacements. We will therefore divide each of these series into a lower division and an upper division, so that those elements with similar general characteristics can be treated together. This classification will be based on the magnitude of the displacement. The lower division in each case including the elements with displacements from 1 to 4 inclusive, and the upper division comprising those with displacements of 4 or more. The elements with displacement 4 belong to both divisions, as they are capable of acting either as the highest members of the lower divisions or as the lowest members of the upper divisions. It should be recognized that in the electronegative series, the members of the lower divisions have the higher net total positive displacement, or the higher atomic number. For convenience, these divisions within each rotational group will be numbered in the order of increasing atomic number as follows. These are the divisions which were indicated in the revised periodic table in Chapter 10. As will be seen from the points developed in the subsequent discussion, the division to which an element belongs has an important bearing on its chemical behavior. Including this divisional assignment in the table, therefore, adds substantially to the amount of information that is represented. Where the normal displacement x exceeds 4, the equivalent displacement 8 minus x is numerically less than x, and therefore more probable, other things being equal. One effect of this probability relation is to give the 8 minus x positive valence preference over the negative valence in division 3. and thereby to limit the negative components of chemical compounds to the elements of division 1. Okay, so he's got division 1 is the lower electropositive, division 2 is the upper electropositive, meaning valence 4 or more, and then division 3 is upper electronegative, again valence 4 or more, and division 4 is lower electronegative, valence 4 or less. And then apparently he's saying that there is also a division, except in one case where a division 3 element acquires the division 4 status for reasons that will be discussed later. When the positive component of a compound is an element from division 1, the normal positive displacement of this element is in equilibrium with the negative displacement of the division 4 element. In this case, both components are oriented in accordance with their normal displacements. The same is true if either or both of the components is double or multiple. We will therefore call this the normal orientation. The corresponding normal valences are the positive valence x and the negative valence minus x. Okay, I believe we will stop it off right there. Now, this is not really that difficult stuff. If you read through this with a copy of the periodic table in front of you, I think you should be able to get this. He's just classifying the elements based on their valences, which have to do with their electric rotations. And get out your periodic table and just go through this again, and you should get it. All right. Have a great day. Thanks for tuning in.